In this video, I'd like to show you how you can use the bilinear or Tustin transform to create digital filters based on analog prototypes. For instance, here I have an STM32 microcontroller running an RC low-pass filter simulation based on an analog RC low-pass filter prototype, and I've used the bilinear transform to get the relevant equations, which I've then implemented in code. This low-pass filter is variable, so I can adjust the cutoff frequency, which we can see on the right-hand side in real time. And you can discretize many different analog systems, such as mechanical systems, low-pass filters, high-pass filters, band-pass filters, or whatever you want, using this method with a pretty good frequency domain match between analog and digital discrete time systems. The system we're running this on is a custom guitar digital effects processing unit, which consists of an STM32H7 microcontroller, various control interfaces via ADCs, controlled via switches and potentiometers. The STM32H7 also interfaces with an audio codec, which contains an audio ADC and an audio DAC, so I can take in guitar signal from my input, feed it through the codec, do some processing in the STM32H7 microcontroller, send it back out through the codec and the DAC and to the output stage. We've seen this unit on this channel a few times before, where we've implemented some guitar effects or general audio effects, but in this video I'd like to show you how you can implement various filters using the bilinear transform, which is a very useful and good to know method. I'll leave some links in the description box below if you'd like to learn more about the system, and I'll also leave a link to the DSP playlist in the description box below. A huge thank you to JLCPCB for sponsoring this video. I had these digital guitar effects PCBs manufactured and assembled by JLCPCB, and they did an absolutely fantastic job. JLCPCB is super easy to use. All you have to do is go onto their website at jlcpcb.com, click on Instant Quote, upload your Gerber data and select options, and you of course can select PCBA as well, and they have pretty advanced manufacturing and assembly capabilities. Not only is JLCPCB very easy to use, but they are also incredibly affordable. For instance, 6-layer PCBs at 50 by 50 millimeters, 5 of them with an Enig surface finish, epoxy filled and capped vias for only $2 and only 5 to 6 days is incredibly affordable, and currently also have up to 8 layers for just $2. I've placed a large number of orders, both PCBs and PCBs with assembly at JLCPCB. I have had next to no issues. They're very reliable as they have an all in-house production and very rapid turnaround. Even with assembly, I can typically have my boards back in about 1 to 2 weeks, which is pretty amazing. Links will be in the description box below. To start off, before we move over to the bilinear or Tustin transform, let's briefly go over discretization basics. When we're talking about discretization, we're basically talking about converting an analog or continuous time system or signal to a digital discrete time or sampled system or signal. This can also be seen as moving from the realm of differential equations, so based on continuous time, to difference equations, which are based on discrete time, so samples. The reason we might want to go from an analog prototype or an analog system to a digital discrete time implementation is because for modern systems, we do a lot with firmware, with software running on a digital system anyway, and we can apply the techniques of digital signal processing rather than having to rely on analog systems, which have component tolerances, which might be more expensive. You can't really change that well on the fly and so on. So therefore, when we're in the digital signal processing realm or the digital realm, we can work with filters, we can work with simulation, we can do modeling of systems, we can do tuning with comparatively smaller effort than doing analog, for instance, hardware designs. These then discretized systems we can run on a digital processor, for example, a CPU, an MCU, or of course convert to a hardware description language and run these on FPGAs. Again, the nice thing is that in the digital domain, we can adjust parameters on the go very quickly. We can very quickly change between implementations. We could, of course, go straight to the digital domain, but oftentimes it's quite nice to go from an analog prototype in the analog domain, for instance, an RC low-pass filter, which we're seeing in the bottom left here, figure out the differential equation, and then convert that differential equation to a digital discrete time or sampled system, because we know approximately the characteristics and behavior of the analog prototype and can very quickly and easily move to a discretized version using a difference equation, and I'd like to show you the process in this video. Another use for discretization could be finding numerical solutions to differential equations when we're doing system modeling, for example, of mechanical systems. We can also do numerical integration, which will be topics for future videos. There are, of course, many methods of converting an analog prototype system into a digital system. We could, again, of course, just go straight to the digital and discrete time realm and compute, for example, filter coefficients directly using optimization algorithms or lookup tables or whatever. Another option is, if we do have an analog prototype, is do response matching. So we feed in an impulse into our analog system, measure the output, and try to match that with our digital system. And there's various different response matching methods, such as impulse invariance, step invariance, ramp invariance, depending on what the requirements are. What I would like to focus on, which I do most often, is using algebraic transforms. And we've used algebraic transforms before, in particular the backward difference method, which is an Euler method. We've used that in video number 20, and I'd strongly suggest checking it out before we continue with this video. That video is called Real-Time Software Implementation of Analog Filters and goes through all of the steps required to implement the backward difference or the backward Euler method. The nice thing is about the backward difference method is that it's quite intuitive, it's easy to use. Essentially on the right-hand side, we can see we're simply approximating a continuous time derivative with a discrete time derivative. So either based on the formal definition of a derivative or using Taylor series and truncating. The problem with this backward difference method is, although it's very simple and straightforward to use, is that, for instance, when we're implementing filters in the digital discrete time domain, there isn't a great frequency domain match between the analog prototype and the discrete time digital equivalent system using this backward difference method. Therefore, in this video, I'd like to show you an alternative method known as the bilinear or Tustin transform, which unfortunately is more tedious to use. It requires something known as frequency pre-warping, which we'll show, but overall it gives a much better frequency domain match than the simpler backward difference method. The bilinear transform derivation is comparatively straightforward, but maybe not as intuitive as the backward Euler method. I'm assuming some prerequisites here. You can feel free to skip ahead to the actual implementation because you don't actually need to know terribly much about this derivation to use this, but I'd like to show you the bilinear transform derivation, and for this you need to know what Laplace transforms are and what the Z transforms are. As a quick recap, the S operator is related to the Laplace transform, and this is also known as the derivative operator, and this is when we're working in analog or continuous time. The Z operator is related to the Z transform and can be seen as a time shift operator when we're working in digital or discrete time. When we're working in discrete time, we also, of course, always have a sample period, capital T. This is a uniform spacing between samples. 1 over t, so 1 divided by the sample period, is of course the sampling frequency. To derive the bilinear transform, we start from the fundamental relationship that z is e to the s times t. And then the inverse mapping is, of course, s is 1 over t times the natural log of z. From this natural log expression, we can simply get the Taylor expansion, and you can find that in books on the internet, and log z is equal to 2 times this expression in the brackets. What we'll do is simplify and truncate. That will just give a first order term, so we'll just take the 2 times z minus 1 over z plus 1 and combine that with this s over 1 over t times natural log of z expression. Combining all of this gives the bilinear transform expression seen below, so s is approximately equal to 2 divided by the sample period times z minus 1 divided by z plus 1. A very nice property of the bilinear transform, similar to the backward Euler method, is that stability between these systems is preserved. So when we're going from a stable analog prototype, for instance, the RC low-pass filter is a stable system. When we move from the analog domain, we implement the bilinear transform, we end up with a stable digital system. When we're talking about S and Z domains, in the S domain, all the left-hand plane holes are mapped within the unit circle in the digital Z domain plane. An issue, however, which we've touched on very briefly with the bilinear transform is that of frequency warping. What we're doing when moving from the analog to the digital or discrete domain is mapping our continuous frequency range from minus infinity to plus infinity to a discrete frequency range, which is bounded, of course, by the Nyquist limit, which is the sampling frequency divided by 2. In addition to this mapping, it turns out if we apply the bilinear transform, and there are many derivations of this, that there's a nonlinear relationship between the resulting frequency mapping. And we can see that nonlinear relationship is something to do with the arctangent, so a fairly nonlinear function. What we therefore need to do, and I'll show you how to do this later on, is we need to pre-warp frequencies of interest using the equation below. So basically this is the inverse mapping of the above expression. So for instance, for the RC low-pass filter, we have a single cutoff frequency, or the minus 3 dB frequency. We would plug that into the bottom formula and use then the resulting new pre-warped cutoff frequency as the cutoff frequency for our bilinear transformed filter. It sounds more complicated than it is. We'll see how to do this later on in code as well. Keep in mind that this pre-warping only compensates at DC and a specified frequency or a specified set of frequencies. If we have multiple frequencies, for example, for a bandpass filter where we have a lower cutoff and a higher cutoff, we have to pre-warp both frequencies. Now let's go through the RC low-pass filter example before we move over to code and implementing this in firmware on an STM32 microcontroller. The first thing we want to do is start off with an analog prototype. And for us, we're just going to start off with this RC low-pass filter with an input voltage x of t in continuous time and output voltage y of t, which passes through that low-pass filter, a series resistor and a parallel capacitor. Since there's no load, we're assuming ideal components. All we have to do is apply Kirchhoff's current laws. So a current balance, the current through the resistor is equal to the current through the capacitor, which we can write as x minus y divided by r, as the current through the resistor is c dy by dt, which is the current through the capacitor. Rearranging that, we get to this differential equation, y plus rc dy by dt is x. Now we want to convert this to a difference equation. We can go with a backward Euler, but of course we want to go with a bilinear transform in this video. Before we do that, we apply a Laplace transform to get the transfer function in the S domain. This is assuming some prerequisite knowledge, but applying a Laplace transform to this differential equation is very straightforward. Our continuous time domain variables are simply mapped to the S domain. So y of t goes to y bar, and every time we have a derivative, we multiply by s. So therefore the resulting Laplace transformed equation is y bar plus rt times s times y bar equals x bar. If you rearrange to get the ratio of output to input, so y bar over x bar, this is known as a transfer function, and from this we can get gain and phase information. If we rearrange this and we collect some terms, we can see that the transfer function is omega c, which is our cutoff frequency, which is 1 over rc. So the transfer function is omega c divided by s plus omega c. So it's a one-pole low-pass filter. From this continuous time transfer function, we can now apply the bilinear transform, remembering that all we have to do is replace every s we see with this bilinear transform expression, 2 over t times z minus 1 over z plus 1, and that then simply gets us to the transfer function in the z domain. And you can see already just by this expression that the math involved is a bit tedious, even for this very simple RC low-pass filter, so you can imagine how this scales for far more complicated systems. In any case, you can follow the math in your own time. I'll leave it on the screen here. All I'm doing is plugging in this equivalent equation for s, and we result in a transfer function in the z domain, again, which is a relationship between input and output. Once we have the transfer function in the z domain, so the discrete time digital domain, we can convert this to a difference equation. And all we have to do is recall that the z operator is a time shift operator. So if I multiply a variable by z, I'm shifting it by one sample time, capital T, forward. I'm going through the math here. Again, you can go through this in your own time. I am doing an intermediate step because I prefer working with z to the minus 1, which is a time delay operator, which means I can then write my final difference equation at the bottom like so. The current output sample y of n is some constant times my current input sample plus my previous input sample minus my previous output sample times some constant divided by some constant. It looks somewhat messy, but it's very simple. We just have to take care of inputs, outputs, and some constants and coefficients. Once we have that difference equation in place, we can't forget to pre-warp critical frequencies. For this particular system, we only have one critical frequency, which is the cutoff frequency of the filter. Remember, omega c, the cutoff frequency, is 1 over r times c in this case, so my RC filter constant. To pre-warp, I simply plug in my omega c, multiply that by t over 2, take the tangent of this, and again, multiply that by 2 over t, and that's my pre-warped cutoff frequency, and that's the one we want to use in the difference equation. If you've watched video number 20, you can see that our bilinear difference equation is a bit more complicated, a bit more involved than the backward Euler difference equation we would get from the RC low-pass filter. In addition, for the bilinear transform, we of course have to pre-warp the cutoff frequency. We have to keep track of one more variable, that is the previous input, and we have to pre-warp compared to the rather simple expression with the backward Euler. However, now let's compare the frequency domain performance between bilinear transform and the backward Euler method and transform. Here I've plotted the Bode plots, that is magnitude versus frequency and phase versus frequency using MATLAB from the discrete time transfer functions in the Z domain. The red curve is the bilinear version with pre-warp, and the blue curve is the backward Euler transform. I've set a cutoff frequency of 100 Hz. The red trace, which is the bilinear with pre-warp, is pretty much bang on that the minus 3 dB magnitude is exactly at 100 Hz, whereas at 100 Hz for the backward Euler case, we're already at minus 4 dB. So actually we have a lower cutoff frequency for the backward Euler. We can also see the magnitude responses are different. The bilinear actually has a better performance for a low-pass filter because we are reaching a far greater attenuation, and also we have different phase performances as well. If we now compare the analog to the backward Euler, we can see these differences a bit more clearly. So the analog is the blue trace, the backward Euler discrete time is the red trace. and we can see there's quite some magnitude differences and phase differences between the two. So it's not a great frequency domain match. However, if we compare the analog to the bilinear, analog prototype to the bilinear discretized system with no pre-warp, we can already see the frequency domain match, even without pre-warp, is a lot better than the backward Euler. Past the cutoff frequency, we are getting quite a bit of discrepancy in both magnitude and phase. But now if we move to the pre-warped bilinear comparison to the analog, at the cutoff frequency specifically, we now have a pretty much perfect match. But above the cutoff frequency, we still have this difference in magnitude and phase, although it is better performing than, of course, the backward Euler method. So it's important to know this frequency pre-warping is really only effective around the frequencies we choose to pre-warp at. With that being said, now that we know the basics of the bilinear transform and how we can go from an analog continuous time system to a discrete time difference equation, let's see how we can implement that on a real-time code and see why this is useful. Once we have the difference equations in place, the implementation on a microcontroller or processor or anywhere in a program is of course rather straightforward. All we have to take care of are the coefficients, which we can pre-compute or compute as we change the cutoff frequency. For example, if you want a variable type filter, and we have to take care of the inputs and outputs. As we can see, these difference equations do have memory requirements. We have to solve, for example, previous inputs and previous outputs depending on the difference equation. Moving over to the C code, I've got STM32 Cube IDE open on the left-hand side. And all we're going to be doing is transferring these difference equations with the coefficient calculations over to some C code. For this, I've created a very simple header file and a corresponding source.c file with a struct, which contains the coefficients for the bilinear implementation and the coefficients for the backwards Euler implementation, so we can compare when we run this in real time. I have some memory for the previous input, I have some memory for the current output of the bilinear, and I have a memory variable for the current output of the backward Euler transform. This struct will then be used as a container for persistent memory across function calls. In terms of functions, I have an initialization function, which pretty much just clears the input and outputs, sets them to 0, so we have a known starting point. The set coefficients function, which computes both the bilinear and the backward Euler coefficients. Again, this is just for demonstration, so we can compare between bilinear and backward Euler. And we have an update function, which computes the actual difference equation, given the coefficients, given the current input, past outputs, and past inputs if needed. Jumping over to the .c file, the initialization function just sets some default coefficients, clears the previous input and clears the current outputs, just so we have a zeroed out starting point. The coefficient function now simply references the slides we saw earlier. For the bilinear coefficient calculation, what we first want to do is compute the normalized cutoff frequency, but of course, since we're running the bilinear transform, we need to pre-warp this. So I'm following the equation on the right-hand side where this omega p is 2 over t times tan omega c times t over 2, which is our pre-warp equation, and for this I'm just including math.h and calling the tan f function. A common term in the coefficients for both the backward Euler and the bilinear transform is this omega c times t term. So what I want to do is pre-compute this omega c times t, which we'll call the normalized cutoff frequency, which is simply 2 pi fc over fs, and fs is the sampling frequency, which is 1 over the sample period, which is 1 over t. If I combine omega c times t with this pre-warp equation, we can see a few of these variables and coefficients actually cancel out, and what we're left with is the pre-warp cutoff frequency is 2 times the tan of pi times the cutoff frequency divided by the sample frequency. So this equation simplifies quite considerably. Once we have this omega c times t term, we can use that to compute the bilinear transform coefficients. So all I'm doing is I'm taking the coefficients which go before, in this case, xn and an xn minus 1. That's my first coefficient. And we can see that is omega c t divided by omega c t plus 2. And this is going to be my first coefficient. Then my second coefficient is going to be minus omega c times t minus 2 divided by omega c times t plus 2. That's going to be my second coefficient, which belongs to this yn minus 1 term. That's all I'm computing here. I'm taking care of the minus signs, so I simply have to do an addition later on. So it's 2 minus omega c t divided by omega c t plus 2. So I'm simply extracting the coefficients before my xn minus 1 terms, and my yn minus 1 terms. Once those have been computed, these can of course be computed on the fly, so I can keep calling this function if I change, for instance, a potentiometer, and I can adjust the cutoff frequency. Then the main function is this update function. This takes in our struct, our low-pass filter with all of the coefficients, as well as the current input sample, so x of n. All we want to do then for both the bilinear and the backward Euler implementations is just follow this difference equation. We simply are plugging this difference equation into our C code and transforming it. Given that we've already pre-computed the coefficients, this is incredibly simple. So our next output sample is our first coefficient times the current input plus the previous input plus the second coefficient times the previous output. And then I'm saving my current input for use next time. It's a simple difference equation. I'm simply multiplying my coefficients by the various terms in our difference equation. So very, very straightforward and incredibly simple once you have the difference equations. For the actual implementation, please reference previous videos, which I'll link in the description box below, talking about the I2S and DMA streams and how to set up all of this peripheral code to get this system up and running. But for now, I'm assuming you've watched these videos. All I'm doing is including my header file in main.c. I'm creating my low-pass filter struct. In int main, I'm simply calling the initialization function and passing in my struct. And in my process buffer, which is called once the DMA acquisition stream has been completed, I'm looping through all of my samples, calling the update function, and depending on the setting of one of my controls, I'm setting the output, the audio output, to be my processed sample, either from the backwards Euler or from the bilinear transform version of this low-pass filter. That's being sent straight to the output DMA buffer. In terms of control, I've mapped my first potentiometer on this particular unit to the set coefficients function, and I've very crudely just set the low-pass filter cutoff to be variable based on the potentiometer setting, so between 500 and 5500 Hertz, and I'm passing in my system sampling frequency, which I've gotten from the clock dividers that feed the I2S subsystem of the STM32. Now let's upload this code to the board and see, first of all, if this code even works, and then look at the frequency response using a Quantasylum audio analyzer. I've connected up this audio unit to a Quantasylum QA403 audio analyzer. I've connected the Quantasylum's output to my DSP unit's input and my DSP unit's output to the input of the Quantasylum audio analyzer. Using this audio analyzer, I'll now leave a link to a video which goes through all of the functions of this audio analyzer in the description box below. But using this analyzer, I can perform a frequency response analysis where the Quantasylum 403 provides a chirp stimulus, and we can extract from that the frequency response information. And in particular here, we can extract just the magnitude response information. I'm passing in a -6 dBV chirp, and we're measuring the output signal here. And currently we are on the bilinear filter setting. We can see we have a flat passband, as we expect, because this is a low pass filter showing down to 100 Hertz. As we increase in frequency, if we move past 1000, 2000 Hertz, we can see the roll-off to start from our bilinear low pass filter. We can see the cutoff frequency, if we go to -3 dB, is approximately 4 kHz. Now I can of course adjust my potentiometer, so I'm going to turn it counterclockwise, wait for the FFT to update, and we can see the cutoff frequency is now moved. Again, looking at the -3 dB point, and that's now at -2 kHz, and we can adjust the potentiometer down even further. And now we can see with this IIR filter, from an analog prototype, we've got a very easy method of creating a variable on the fly filter. So now we've set our cutoff frequency to about 500, 550 Hertz. So if you want a simple implementation, you might just go with the backward Euler. If you want to have a better frequency domain match with more involved calculations, you would go with the bilinear or Tustin transform. Thank you very much for watching this video. I hope it was helpful in understanding the practical applications of the bilinear or Tustin transform and how you can use it to start from analog prototype systems and convert them into discrete digital time systems, which you can then run, for instance, on various microcontrollers to do signal processing with. If you like the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest hardware design, embedded systems, and general electronics videos. Thanks again for watching, and I hope to see you in the next one. Bye-bye.